Hello, it has been a while since our last math class, so I'm making this video to help you review a bit before we meet again. We are going to be reviewing trigonometry, and the first point that we need to review is trigonometric ratios in right-angled triangles. So we have here a right-angle triangle, and I'm going to fix one of the angles that is not the right angle. This one over here with blue, I'm going to call it theta. Once I fix the angle, I'm going to have one of the legs that is next to it. I call it adjacent to theta. And then we have another leg that is opposite to it, and so we call it opposite to theta. And of course, then the third side that we have over here is the hypotenuse. Once we give those names to the three sides of the triangle with respect to the angle theta, we define the trigonometric ratios sine, cosine, and tangent. To define the sine, we need to find the ratio between the side opposite to theta and the hypotenuse. So this is in our SOHCAHTOA, the SOH part. To find the cosine of theta, we need to find the ratio between the side adjacent to theta and the hypotenuse. So this is the K part of SOHCAHTOA. And then we have the tangent of theta given by the ratio between the side opposite to theta and the adjacent one, and that's the TOA. So these are the three definitions that apply only to right-angle triangles. We use them to find sides or angles of right-angle triangles. We use the calculator to find the angles using the sine inverse, that is denoted with sine with a -1 upper index, the cosine inverse, and the tangent inverse, were the inverse functions to the ones that we defined at first. If you feel that you need to review how these sine, cosine, and tangent functions are used in right-angle triangles, I recommend that you watch the videos that I made to comment on the assignments, on the last assignment that I corrected. With the help of the calculator, we have seen as well that we can work with the sine, cosine, and tangent functions outside right-angle triangles. This means that we can find out what is, for instance, the sine of an angle of 98 degrees, even though an angle of 98 degrees doesn't live inside a right-angle triangle, and hence we cannot use the SOHCAHTOA definition that we have. You can still ask your calculator what is the sine of 98 degrees, or you can ask your calculator what is the cosine of 122 degrees, or even what is the tangent of -17 degrees. So please pause the video for 1 minute and check that you can find what these values actually are. Your calculator knows how to do it. I asked my calculator what are the values of sine of 98, cosine of 122, and tangent of -17. And I wrote the results here using three significant figures to approximate. So hopefully you can check that you got the same result. Something else that is worth noticing is that if here we decide to find what is the sine of 82 degrees, we'll get the same result as when we found the sine of 98 degrees. The property that is in play here, we have seen it in class before, is that if we have two angles, let's say alpha and beta, with the property that their sum is 180 degrees, as we have over here, 98 degrees plus 82 degrees is 180 degrees, then the value of the sine of alpha is going to be the same as the value of the sine of beta. Now, something that we have to take into account is that when we type that value in the calculator and we use the sine inverse, so when we ask the calculator, what is the angle that has a sine of exact 0.990? So the result that we got for both angles. The calculator is going to tell us that that angle is 82, which is true. But it's not telling us all the truth, because we have to remember that 180 degrees minus 82, so the angle of 98 degrees we started with, is also going to be a possible solution for the sine inverse of that value. So this is something that you have to take into account and you have to remember. Now, I know that there is quite a bit of information here, and there is quite a bit of believing in me, because actually we don't know what it means sine of 98 degrees or what it means sine of 122 degrees and so on. So I'm asking you to believe me that this is something is worth working with, and we can do it with help from the calculator. And very soon, probably in a couple of weeks, we are going to know a little bit more about what's going on over here. The third thing that we need to review is the formula to find the area of a triangle. Note that the triangle that I drew over here is not a right angle triangle, it's just any triangle where we know that one side is P, another side is Q, and here the angle between the two sides that we know is the angle alpha. So then our formula says that we can find the area as a half times the length of one side times the length of the other side times the sine of the angle between the two sides that we mentioned before. We are going to solve some examples. The first one I ask you to solve is this triangle over here. We want to find what is its area. We know one side is 7 units, another side is 8, and the angle between those two sides is 87 degrees. So we can just go ahead and apply our formula. So the area is going to be given by a half times 7 times 8 times sine of 87 degrees. So you should pause now and see what you get in your calculator when you try this. I got 27.96, and then the number continues. I don't care about what continues because I want to approximate to 3 significant figures. So this number fourth figure is gonna be the 6. That changes the 9, so I approximate this to 28.0 units square. In our second example, we want to find x, the measure of one of the sides of the triangle, knowing that the area of the triangle is 29 square centimeters. Here I should add the lengths are in centimeters to make this reasonable. So what we know is that by the formula for the area, 29 is going to be the same as a half times 10 times x times sine of 35 degrees. And now you pause the video so you can find x by isolating it from this equation. And you can check that the result for this value of x is 10.1 centimeters. If you are planning to do math studies next year, you can stop the review here. If not, let's go to example number 3. For our third example, we wish to find the angle alpha, knowing that the area of the triangle is 20 square meters. You will see over here that the sides next to the angle alpha are 7 meters and 8.5 meters. So applying the formula for the area, we have that 20 has to be the same as a half times the length of one side, 7, times the length of the other side, 8.5, times sine of the angle alpha. If we isolate the sine of alpha, we get that 20 divided by a half times 7 times 8.5 is the sine we are trying to find. So we can ask our calculator, applying the sine inverse of this fraction, what the value of alpha is. I hope your calculator and my calculator agree that correct to 3 significant figures, alpha has to be 42.2, or if we remember the discussion that we had before about the calculator only giving us one of the possible values for the sine inverse of a number, we could also have that there is another angle possible, alpha 2, that is given by 180 degrees minus alpha. So this will be 148 degrees, correct to three significant figures. Now, how could this happen? Let me show you a picture. We have the sketch here of two possible triangles that both have an area of 20 square meters. Both have one side to be 7 centimeters, the other to be 8.5 meters. But the difference between the two of them is that between those two known sides, in one of them there is an angle of 42.2 degrees, so it's an acute triangle, and in the other one there is an angle of 138 degrees, so it's an obtuse triangle. But since the sine of those two angles is the same, the area of the triangle is the same. And then we have two possible solutions for our problem.